Once again, welcome everyone, wherever you are in the world, to the webinar put on by MedPharmPlast Europe concerning circularity and sustainability in MedPharmPlastics medical devices and pharmaceutical packaging. I want to turn the floor over to the president of MedPharmPlast Europe, Frank de Smet, who is working with Nelson Labs here in Belgium. So Frank, over to you, sir.
Thanks, John. Yeah, I will not take too long, but I would like to welcome you all in the name of MedPharmPlast Europe, but also in the name of Polymer Comply Europe, which we do together this webinar on circularity. We all thought, I think, that in December of this year we would have gone back to normal again, or let's say more or less to a more normal situation. But unfortunately, the other wave of COVID has hit us again. For the webinar online itself, it doesn't matter, of course, but let's say to see each other, to network and to talk about all the things in our sector group, it's still a little bit, yeah, Stone Age in this way, because we like to meet and interact. Especially because in our sector, things are not standing still, of course. Life goes on, it evolves, it perhaps even accelerates in some topics. If I think about all the things with medical devices and medical device regulations, but also requirements for raw materials or packaging. We are in a sector, the pharmaceutical packaging for certain, with quality aspects, but change control and so on, and changing regulations on which additive is allowed, which is not. A lot of things change, and for sure, sustainability or circularity are things which are on our plate every day and will become very much important and alive and have to have our attention. And in that sense, it's okay, and it's logical that we have put a second webinar in place. And we did the first one in June, beginning of June, on circularity. We saw that there was a lot of attention for it, a lot of interest, and that's why we have today the second one, which will be moderated by John, with a lot of speakers from different areas who can again highlight us or introduce us in some of those aspects of circularity and sustainability. So John, the floor is yours.
Thank you, Frank. Thank you for that, Frank. And okay, so we'll get started with the speakers here in a moment. I just have a couple of things I want to say to kind of, if you will, set the scene a little bit. Let me see if I can share my screen. This is always the big test for me. So let me know if you see something, a lady sucking on an inhaler. Do you see that?
Yes.
Okay, so here we are today. So welcome to the webinar again, and thanks to all you participants out there. I know that this is a very busy time of the year, and to take even a couple of hours out of your time to join in on this is really a commitment. So thanks for that. And as Frank said, we have a list of really interesting speakers, interesting topics, beginning with Lacey Linney from Cytiva, then Benjamin Porter from Trinseo, and then finally Marco Tomasi Morgano from Arcus Green Cycling Technologies. So really interesting speakers and subjects. Before we begin, though, I just want to kind of position a little bit of why we're here. This seminar, this webinar, is not a webinar that's on the subject of recycling. It's not on the subject of chemical recycling. That is not the subject of our webinar. This is not the case. What is the case, however, is these technologies are critical whenever you want to have a discussion on circularity and sustainability in MedPharmPlastics. And so this is not the subject, but it is a big part of what we'll be talking about today. So just that in mind. And like I said, we will be talking about design with Lacey. So looking at not just recycling, but obviously when you talk about design, you talk about the other two R's: reuse, reduce, the other way around, and then recycle. So we're covering the whole R's, let's say. So that's it. Let me say something about the importance of recycling. However, this is relevant to us in the MedPharmPlastics value chain. So bear with me looking at this slide. You can see what is the demand development of polymers globally up to 2050. This is from McKinsey from some years ago. And what's interesting when I look at this is you see the very bottom, where you have virgin feedstock. That's polymer, that's fossil fuel-based polymer, right? Fossil-based polymer. And if you see this graph, you see in the mid-2030s, it starts to plateau, and then finally in 2040, actually we start to decrease the offtake of virgin feedstock to make polymers. So that's what we're looking at moving forward. And why is recycling important? It's because in order for us to do that as a society, we need the recycling technologies to enable this. The light green at the top is mechanical recycling. Most people are able to kind of grasp what that is conceptually and practically. That is an established family of technologies you see there. And if you see over time, you see the other two blue sections, recovered monomer and recovered feedstock. Let's just put those together and call that chemical recycling. And what you see, of course, in the coming years, 2030 to 2035 to 2040, you actually see parity, meaning that you'll have about an equal amount of chemical recycling taking place as mechanical. And so this is what we see moving forward, and the importance of recycling. And then when you apply this to the MedPharmPlast sector, it's even, I think, more interesting because in MedPharmPlastics, what we know is when you mechanically recycle, you're not able to use it again for the same application. And so this is also why we think that chemical recycling maybe is of particular interest in the MedPharmPlastics sector, because it's through chemical recycling and renewables that you're able to enable circularity. So that's why it's important. We'll talk about that. This slide's a little blurry, but it's just to give you a picture of the landscape here in Europe for chemical recycling. This is circa 2021, September, just a few months ago. It really is that dynamic. It's changed since then, and it just has not been updated by me. And just the looking around here, you see the blue dots represent the technology of pyrolysis, which we'll talk about more later on. The red dots are depolymerization, another type of chemical recycling technology, and then some others here. I put this here to show you that, especially in the Benelux area in Germany, you see just growing mushrooms of announcements and capacity that's coming online for chemical recycling. And the four blue dots that are in the Atlantic Ocean, these are not floating chemical recycling facilities. These are their announcements of siting new facilities in Europe that have not been specified the location. So just a little bit of how dynamic this sector is that we're going to be talking about some today. And then that being said, it brings me to our first speaker. And if I may kind of set the scene for our first speaker. Our first speaker is Lacey Linney. She works for the company Cytiva, and I'll let her, if she wishes to tell a little bit more about Cytiva, its origins coming through GE over the years. And she's responsible for evolving plastic and design and sustainability, leading these efforts at Cytiva. And so she's the perfect person to come here today to talk to us about design in sustainability in MedPharmPlastics. And I want to thank Lacey for coming today, and I want to give her especially a thank you for getting up at so early in the morning. Lacey's based in Washington State in the US, so she's 9 hours away from CET time. So it's now 6:10 in the morning. So with this being said, Lacey, I will turn the floor over to you, and welcome.
Thanks, John. Appreciate that.
Okay, I need to stop sharing, and then you can start sharing. So.
Okay. Okay. So thank you everyone for having me today. It's really nice to speak to everybody, and I look forward to the Q&A later in the presentation. As John said, I am the Evolving Plastic and Design in Sustainability Leader for Cytiva. I've been with the company for almost 14 years, but moved into this dedicated sustainability role in February of this year. So we're actually going to start with introducing you to who Cytiva is. A little bit of our background is that we were formerly GE Healthcare under the life sciences umbrella, and we moved out from underneath GE in about 2 years ago also. And as of very recently, we are now a part of the Danaher Corporation. So let me escape from my presentation really quick. I'm going to take you to the internet. So this is our webpage, but I would like to just share a quick video with you about our company. First, were you able to hear the sound?
Not yet. Can you please? No.
I should have tested this. Okay, hold on one second. Okay, well, we'll just go on without the music, but please check out our website if you'd like to hear the background music. The message is in the video itself, so let me restart that. Awesome. So a little bit more about us is that if anyone you know or yourself has had cancer, or if you have had the COVID vaccination, there's a high likelihood that Cytiva has been a part of the development of those therapeutics as part of your healthcare solution. So we're happy to be here. So let's jump right into our sustainability plan. About 2 years ago, we had a senior leader announce a company-wide initiative related to sustainability. He really recognized the importance of this for our business, and about 17 people volunteered their time, and we met in early 2020 and drafted an initial set of priorities and kicked off a lot of projects related to sustainability. Throughout 2020, we worked on refining these priorities and really began to understand what it meant to commit to sustainability at a corporate level, and landed on 2 major impact areas. Of course, we want to focus on people. We want to advance healthcare, which is very much aligned with Cytiva's mission statement. And also we wanted to increase the diversity and inclusion across our entire business, and especially at key leadership levels. We can't deliver on any impact without a strong foundation, and foundation is rooted in innovation, responsible sourcing, as well as a strong ethics and integrity backbone. And of course, we want to attract the right talent and encourage engagement across our business. At the center of our sustainability plan is designing in for sustainability. We recognized pretty early in the process that if you don't have a company-wide adoption of sustainability, then the odds of it being successful are probably pretty low. For those who aren't familiar with the term design in or designing in, this is literally integrating a concept across a product or a process, or excuse me, integrating a concept or product into an existing process. So what we want to do is design in sustainability to the core of everything that we do. Recognizing something that you have to change at the core of a business is really a cultural shift. We have to weave it into the fabric of our business across all functions and all leadership levels if we're going to be successful. We are asking all 8,000 of our employees to own integrating sustainability into their role, and we really don't think we'll succeed without their buy-in. We recognize this is not going to be easy. It's going to be a long journey that we are just at the beginning of, but we are committed to supporting our associates and our teams through training, providing them with tools to help them make the right decisions, and build a network of sustainability, build a network where people can converse around topics and celebrate solutions and recognize expertise in specific areas. So I have a quick question for the audience. Hopefully you guys are hanging in there with me so far. Are you seeking out products or services that have sustainable design or features? I don't think I'll be able to see all of the chat going on, but it's really just a question to pose to you and give some thought about. Okay, so here at Cytiva, we are definitely seeing an increase from our customers requesting sustainable design features. Our entire industry is seeing that pressure, so we are hoping to integrate sustainability early so that we can start responding to these demands and be more proactive instead of reactive. So roles and responsibilities when it comes to designing in for sustainability. We really focused on the first phase of designing in with our new product introduction framework. It's essential that all functions identify where their impact area is and look to integrate that throughout the NPI process. For example, product management is the voice of the customer. We are encouraging our product managers, our marketing leaders to go seek out conversations with customers related to sustainability. It's important that we have our customers' voice as a part of the NPI process so that we are designing in for their needs, and it will make conversations with them much easier if we can align on sustainability priorities, both as a business and from the customer perspective. The project leader. Project leader has to make time to have discussions around sustainability. You cannot fit in sustainability at the end of a conversation around a new product. You have to integrate it and you have to dedicate time for it. Give space to people to innovate and brainstorm when it comes to sustainability, when it comes to increasing efficiency and reducing waste. Engineers, really strong, going to have to be strong in this presence for designing it for sustainability, going to be a huge opportunity to design out waste. And then manufacturing, of course, we want to see manufacturing efficiencies increase and also reducing waste. The responsibilities that I'm showing you on the screen are related mostly to new product core teams. But we cannot deny that as we move through our journey of designing in for sustainability, that it's going to impact a lot more roles than just the people on this list, right? I mean, we want to have human resources have a way to integrate sustainability. We want to include finance, give them the tools and help them understand the decisions that we're making related to sustainability. And we can't forget, our field teams who are experiencing waste firsthand when it comes to package delivery and things like that. The important part is that we are really looking to challenge our team members and challenge each other to think outside of their function, think about break down those barriers so that they aren't just thinking, okay, I'm looking at this one piece of this process, and instead together as a team challenge each other to look for increases in efficiency. We are asking each of our team members, specifically as part of our first phase of framework launch, how they are going to integrate sustainability into their role in 2022. Our design-in framework is really based around the circular idea of a product lifecycle. We are challenging our team members to look at every piece of the life cycle, not just look at raw materials and then hand it off to manufacturing, who hands it off to packaging or warehousing. Really, we want to look at everything all the way through the end of the product life or its disposal. Our framework is built with simplicity in mind, as John already mentioned. Our framework is based around the idea of reducing, reusing, and recycling. This is terminology that's easily recognizable, and it does simplify how to approach sustainability throughout the design process. For example, raw materials. We want to challenge our team members to think about using and sourcing recycled materials as part of raw materials. We want to encourage them to make good decisions about chemical choice, and then other topics like using non-virgin wood materials and utilizing local suppliers to reduce carbon footprint. Manufacturing, as I mentioned, we want to integrate efficient manufacturing processes, whether it's on a product or a consumable. We want to look to reduce energy, waste, and water needs when possible. For packaging, there is a huge opportunity to improve packaging. I think we as consumers have witnessed some really great examples of smart packaging and just efficient packaging. And I would love for Cytiva to start integrating some of that, where it's really designed around the product, using recycled materials, but reducing waste and reducing packing materials. Of course, we also want to think about using non-virgin materials when possible and ensuring that those materials are recyclable at the end of life. And distribution. The weight of a product is directly correlated to CO2 emissions. So any opportunities to reduce waste, avoid temperature sensitivity, which would require cooling or heating as part of the shipping and storing process. We also don't want to be shipping air around the company or around the world. So again, another opportunity to really increase our design for our packaging to reduce our carbon footprint as a company. And then use. We have to think about how the customer is using it. Are we making energy efficient products? Are we looking to make them water smart products? And then also, thinking about circularity and extending the life of a product. We want to design in for modularity so that parts can be replaced and pieces can be replaced, extending the life instead of the full instrument needing to be replaced. Oops, wrong way. And then disposal. You cannot ignore the fact that we need to recycle more. So we need to think about how are our users going to disassemble our product, our consumable, for ease of recycling. And we also need to make sure that we are labeling as often as possible, communicating the makeup of our products so that customers can have a clear direction on what to do with it at end of life. The first half of this year, we piloted our design-in framework with early stage NPIs, as I stated, and really had a lot of great feedback that helped us streamline and get to this circular perspective on design-in. We saw innovation, we saw engagement, we saw teams, welcoming the challenge of solving big problems together. So hopefully we'll see more of that as we move forward and expand this to more products within our portfolio. And I am happy to say that we are on track to launch the first phase of our Design-in for Sustainability program on January 1st. So looking ahead at 2022 and beyond, we have to integrate rigor into the processes that we're implementing. We have to support the teams that are being introduced to sustainability. We have to build that network that I mentioned earlier of expertise and tools and resources. And not most importantly, but extremely important, is celebrating the successes. We have to acknowledge the wins and we have to share the stories so that other people feel empowered to take on Design-in for Sustainability within their role. From my perspective, it is absolutely necessary that we integrate design for sustainability for the future of our business. I'm going to leave you with a quote from our President and CEO, Emmanuel Lignier. Sustainability is key to the future of any organization. At Cytiva, we know that we are guardians for the next generation, and I could not agree more. And with that, I want to say thank you for listening in on my discussion for about 15 minutes, and I would love to answer any questions you might have.
Thank you, Lacey. Can you hear me, Lacey?
I can.
Okay, thank you. Thank you for that presentation. I thought it was really, really good and interesting, and really great to kick off the webinar here today. Now I'm gonna go to some questions that have been raised, and I'm new to these online questions, so bear with me if I make a mistake here. But there's one that's come up from oh, there's another one that's come up. I'll read it to you, and then I'll say answer live and see, maybe you see it. But the question is, well, first, really like the design and framework concept. Thanks for sharing. And based on your learnings, what advice would you give to others embarking on a similar journey? So you have an audience here that's saying, hey, interested, give us advice, please, Lacey.
I would say really the first piece of being successful or launching something like this is leadership buy-in. Having an advocate at a certain level of your business that can influence senior leadership at the top level is extremely important. That's why we were successful in kicking off sustainability. Then when it comes to design in, it's really about over communicating. It's about checking in with different functions in the business and just continuing to say, this is what we're planning on doing, give us feedback. Like I said, we're really early in designing in for sustainability, but we've gotten so much support just by continuing to have these calls and pull in stakeholders and check in with leadership.
Okay, thank you for that, Lacey. Another question is coming that I'll read to you is where do you think, where do you see the greatest opportunities for sustainability improvements? Of course, within Cytiva, but maybe based on what you're doing at Cytiva, you can make some general comments for others as well.
One of the biggest opportunities for us right now, which is very present, is examining our supply chain and the flow of products around the globe for us. We really are revamping how we ship product, how quickly we ship product, and trying to simplify that process, do more for sourcing locally and building locally so that we aren't shipping all over the world. I think we have a really huge CO2 reduction opportunity. I also think packaging, I already mentioned this, I think there's a great opportunity in packaging to reduce out a lot of waste. And then thinking more of the future state of opportunities, I have to believe that there's a bigger opportunity in recycling. It feels like healthcare and life sciences has been an exception to the pressures that comes with recycling. You know, we are an important piece of everybody's lives, so it's okay for us to sit kind of removed from all the pressures of recycling, but we use so much plastic. So I have to assume that the future state of healthcare and life sciences is that we will have solutions for our plastic, mixed plastic, even contaminated plastic. So fingers crossed for the future of that.
Excellent, excellent. Hey, another question that's kind of related. Does Cytiva have any plans for product recycling or product take back? So in this sense, I guess, closing the loop. So,
gosh, at this point, I can't say that we do, but we have to explore all options. And probably this has been said by John a couple times, right? We cannot ignore every opportunity. So will this be something we try to integrate in the future? We have to look at it. I think take back programs are a great way to extend the life of products. It's a great way to reduce waste. So we will need to look at it.
Okay, all right, thank you. And then one last question here that I see coming up is, and also I was also curious, the mention of non-virgin wood. Can you say something about that application? Okay, wood is not plastic, so it's a little bit beyond the scope, but can you give us a few seconds on that?
Sure, it's really just seeking out recycled product instead of using virgin wood, or seeking out wood that is not from an impacted or high impact areas such as the Amazon. It's just making sure that if you're seeking out if you're seeking out pallet use, for example, there's ways to not use, there's programs out there that will reuse the wood pallets and create new pallets. There's also a big opportunity to use reusable plastic pallets through mechanical recycling, which extends the life of those pallets. So yeah, it's really just about not continuing to suck up new resources.
Okay, thank you. I see we still have a couple more minutes, so I'm going to take advantage of the time here. Another question that's come up, I find a really interesting one. What do you see are the biggest material challenges when you talk about design and sustainability? I mean, can you comment on that?
It's probably plastic.
Yeah.
It is extremely, the design of products in our space in life sciences, in healthcare, is extremely important that it's clean, that it's validated, that it's qualified, both for our processes and even for the companies that are manufacturing vaccines and therapeutics. So for us to make a design change, it's going to take us a long time to get qualified, get validated, integrate changes with our downstream manufacturers. So we have to start thinking about what other options there are for plastic, if there is, if there's design changes that we can make, but this timetable could take anywhere from 3 to 7 years. And we've already set targets for ourselves for 2025, and we have some gray ones in the background for 2030. So it's something we have to start tackling next year.
Okay. Well, we have several more questions here, and what I will do is keep these questions, and when we have the panel discussion at the end of the speakers speaking, we'll try to come back and answer more of these. But we got plenty of really interesting questions here, Lacey. So I'll park these for the moment. Hopefully, I will not accidentally delete them or anything like that, and then we'll move on. So thank you very much, Lacey, for that presentation. Thank you so much.
Thank you.
Okay, so it's we're pretty much on schedule. Actually, I'm looking at my time here, and actually I see that we still have another couple of minutes that we could spend with Lacey. But what we'll do, since I already got the ball rolling, we'll go on to the next speaker, and then we'll pick up on these questions for Lacey with the panel discussion. So that I'll move on now to our second speaker. Our second speaker is representing the company Trinseo, and I'll let him, of course, introduce more his company to us and what they're doing and their role in the MedPharmPlastics value chain. Benjamin is a speaker today. He's an industrial engineer, studied in Hamburg in Germany. He's been working in the plastics industry since 2009, so 12 years. He's worked with all different types of materials, biopolymers, polycarbonates, styrenics, TPEs, including TPUs, and focusing on different markets, including, of course, the medical sector. But they also offer their offering to different sectors, not surprisingly, electrical, lighting, cables, personal care, toys, etc. Today, the focus is on medical. And Ben is working as business development manager for Trinseo today. So Ben, if I may turn over the floor to you, and we look forward to your presentation.
John, thank you for the kind introduction, and also welcome from my end to this webinar from MPPE. I'll start sharing then. Please give me a shout in case you can't see it. Otherwise, I'll get started on the topic I'd like to share with you today. Trinseo is a material provider, and within Trinseo and our activities as a granules producer, we would like to share some insights on options that we think are applicable to the products we have in our portfolio, and the different routes, the different approaches we follow on bringing circular products onto the market. Before we start, just a brief introduction into Trinseo, in case you haven't come across Trinseo yet. Let's see if I can get this one. Can I get this one? Well, it seems this remains okay. Never mind. Trinseo is a spin-off from Dow Chemicals. We are 11 years on the market. Started 2010, as you can see here. At that time, we took over the styrenics and polycarbonate business, completed, or let's say, enhanced the offering with TPEs through an acquisition we've done in 2017, ARPI, a TPE compounder in the north of Italy. And then this year, we completed the acquisition of Arkema's PMMA acrylics business. We are a US-based company, and with about 3.8 thousand employees, we generate about 3 billion net sales. These are some products that we have. You can see we have, besides plastics, also other materials in latex and in binders. But the matter that I'd like to talk about you today is within plastics. Some of the trade names are trade names familiar from the Dow times, such as the Caliber polycarbonate or the Magnum ABS. But you can also find Ultraglass and Plexiglass in there, the PMMA grades that we've recently added. Not to mention also Megold, our TPE CBS based. On the right, you can see some typical application that you would use these materials for. You can think about PC ABS, flame retardant into housing, or even PC polyester blends such as PC PET. A typical housing could also be made from an ABS or a drug delivery device, not to mention the dialyzer, which will be a polycarbonate application, for instance, or the tubes made from TPE, and completed on the bottom with some diagnostics products which can be made in transparent polystyrene, for instance. Now, let's move on to sustainability and some insights that we would like to share with you when it comes to medical devices. First of all, just a small introduction on the market environment that we're targeting. Obviously, we are all aware that the medical field is one of the most regulated markets, with multiple notified bodies involved in Europe and North America and others. We have pharmacopoeias, device directives. We even get asked down to food contact safety. Biocompatibility is a common vocabulary. And why is that? Because the industry focuses on managing risk, making sure that the quality that has been validated and qualified remains the same throughout the process, and the part of the article performs throughout the lifetime. That's done with a significant amount of quality control, obviously, and that has then implications when we talk about sustainability and which approach to pursue. And last but not least, when it comes to products used in medical, obviously we use plastics in single-use devices, but also in durable devices, in machines, in equipment, in monitors. But besides that, there are also other plastics involved, or other materials used beyond plastics, such as glass for vials, for instance, or paper in packaging, as we mentioned earlier. Yeah, these all make the circularity of materials obviously more challenging. Now, these are some numbers I've picked from Plastics Europe, dating back to 2019. What you can see here are the European consumption of plastics split by polymer group. And no surprise, the biggest fraction is polyolefins. What I'd like to share with you today are some insights on polystyrene, SAN and ABS products we manufacture, together with polycarbonate, and last but not least, PMMA, as well as other plastics. It wouldn't surprise me if the relationship, or let's say the amount of plastics used specific in medical, let's say the ratios wouldn't differ significantly. Obviously, the amount of plastic use will be significantly smaller, but not the ratio, I would say, than it is displayed here. So obviously, when it comes to circularity, a lot can be done with looking at polyolefins, and you can see that's no surprise that there is a lot of traction happening there. But with my presentation today, I would like to share some insights on the styrenic spaces, which, although they're small, they're still mentioned here, so I think they have a valuable contribution to play. First of all, I'd like to share with you that when it comes to styrenics products, Trinseo is part of a industry-wide consortium called Styrenic Circular Solution, which brings together partners from the supply chain around polystyrene. You can have producers of styrene monomer, people or companies who polymerize it, converters down to recyclers, with the idea to convert polystyrene post-consumer into virgin polystyrene again. It's been started in 2018, and we believe Trinseo plays a vital and an active role in this consortium. Why do I hammer so much on polystyrene? Because it is so core to our business, and it gives a nice example of what can be done with the different routes. Why is that the case? Well, if we look into polystyrene, obviously we have the linear business model that is familiar to everyone here, and the circular business model is then, let's say, the expansion to that. Now, Trinseo, I would say, would sit somewhere around here, producing polystyrene, but also generating the styrene monomer. These granules get then shipped to converters who make then articles, starting or ranging from a food packaging to insulation boards, over to toys, and eventually also medical packaging. At the end of the life, it gets collected and then sorted, and this is where the new routes of bringing circularity of polymers starts. First of all, you could think about mechanical recycling. As John mentioned in his introduction, mechanical recycling is a well-established route, and it has its justification demonstrated decades ago. And with the, let's say, enhancement of what we call the super clean mechanical recycling, we might bring even some extra value. What's this all about? This is essentially the adoption of what is known from PET bottle recycling. So at the beginning of this process, you start with, let's say, a purity of 97% of polystyrene, with some extra washing and purification and sorting steps. You can achieve, it's stated here, up to 99.9% polystyrene. With this high purity, the consortium is currently investigating to see whether we can get European Food Safety, the European Food Safety Authority approval, FCSA as stated here. That can be adopted to polystyrene currently, we believe, in a quite easy way, as most of the contaminants are filtered out, and that can be a viable solution within the mechanical recycling stream. Another mechanical recycling idea would be through dissolution. What you do here is you add a specific solvent that then dissolves the polystyrene into a viscous slurry, which we can then feed into our polymerization tanks. With this route, you can achieve up to 30% post-consumer polystyrene that we can add. Remember, again, it's a fairly viscous slurry. It's quite difficult to add more from a technical point of view. Also here, at this moment in time, it is not yet food approved, but we achieve similar purities, and this is used, I'll show you an example in a second, and in a non-critical food application. So the question to the audience here is, couldn't this be a viable idea also for, let's say, some secondary packaging in medical, which do not have, for instance, contact with the patient or the operator or the drug? And here you can already blend in a little bit of more sustainable material. The next building block, which is really appealing for polystyrene, is around depolymerization. The chemistry of polystyrene is so simple that, in fact, you need a catalyst and a little bit of heat. And then as of 350 degrees Celsius, it starts to unzip the polymer into its monomeric building blocks. That is obviously a very interesting route. You can then achieve what we call a potential upcycling. So you go from food grade down to up to food grade again. And obviously you receive then a styrene monomer quality, similar, if not the same, I would say the same, with the same specification as the virgin styrene monomer. So with this, let's say, new stream of styrenic monomer, you could obviously create a new polymer, polystyrene, but you can make multiple other things. Polystyrene is one of the few polymers that is so easy to be depolymerized. Another might be PMMA. That this route is a very interesting route that will come online in the next years. To complete the picture about what we consider chemical recycling, there is also feedstock recycling. I won't touch on this in great amount now because the speaker after me, Michael, he will share his insights in great detail around the second idea, feedstock recycling, which will be most applicable to other polymers, not to polystyrene, eventually also polystyrene, but predominantly to others. Here is an example of a first food contact application. You can see it is a yogurt cup packaging where the diluted material is used in the core of an ABA structure. So the material is not in direct contact with the packaged food, and it is therefore good enough to be applied, although the ESCA approval is still pending. And I think that's an interesting approach to see, okay, let's get down to the application, what was really needed. Can we do something around it? And here, there's a core layer that already consumes 30% of post-consumer recycled. I think that's a great success story here. Now, it's not only Trinseo that invested and discovered that chemical recycling of polystyrene is a great advantage of this polymer. There are multiple other players throughout the industry who are doing the same. You can see here, first commercial plants are coming online in 2022, 2025 from different players, which will make polystyrene a fairly sustainable polymer. In total, there will be around 43 kilotons of recycled styrene monomer available by 2025. And together with the dissolution and mechanical recycling, the total amount will be about 150 kilotons of recycled polystyrene. That's a lot of medical devices you can make from them. So I think this is really picking up, and you should see more and more coming on board around recycling of polystyrene. Now, obviously, when you have the styrene monomer, you can then decide what to do with that. And one idea is to use it in copolymers, such as SAN or ABS or SMMA, if you like, or you could use it into a rubber, a styrenic-based rubber, or even into thermoset rubber, if you like. So there are multiple options opening up with the creation of a recycled styrene monomer. Not only that there is a circularity achieved within the styrenics, we also started to generate some environmental data within the Styrenic circular solution. And as you can see, from an environmental point of view, it's no surprise that the mechanical recycling have the greatest benefit in terms of CO2 savings. In fact, the super clean mechanical recycling reduces the CO2 footprint versus a virgin polystyrene by 80%. This solution and depolymerization also have a great benefit when it comes to CO2 savings. Now, we've touched on one idea about circularity, how to bring that into these specific polymer. Why did I start with polystyrene? First of all, it's the first polymer that we've greatly investigated, and we've made a commitment to invest into a first polymerization plant. There will be other polymers where similar recycling ideas and concepts will be evaluated. Starting from the well-established mechanical recycling for industrial application, I think it's good enough for a lot of application. That's also where the image about recycling comes from. It tends to be in rather dark or black colors. And for some application, it might be good enough. But we are today talking about medical application. What I've tried to bring across to you today are the new options that will come online, such as super clean mechanical recycling, the dissolution with up to 30% of post-consumer recycle being consumed here, and also depolymerization of polystyrene, where we achieve a pure virgin-like styrenic monomer. Now that already helps us to bring circularity into the existing business. And in that respect, I think plastics are fantastic materials if you compare them to metal or glass or others, because in general, there's a lot less resources and energy used. But beyond that, you can also consider what is then entering into the cycle here. And of course, most of the plastics nowadays are based on fossil fuels. What about introducing different sorts of renewable resources? Now, obviously, some of them have been around for decades. Think about materials based on cellulose or bio-based polyamides. Recently, there's been addition also fairly recent from bio-based polyethylene from Braskem, for instance. Not to mention PLA from NatureWorks, to give you some examples on polymers which are truly bio-based. What is fairly new to this concept is the mass balance concept. And for those who are not familiar yet, I'd like to give you a few ideas about mass balance. Essentially what it is a concept applied or copy and pasted from green energy. What we have today is a given infrastructure. And of course, what you can do is you build an extra infrastructure with sustainable sourcing. But as you can imagine, that is not very sufficient, because at the end of the day, you would have the double infrastructure with the double investment. So instead, and that's the second idea here, most of the polymerization processes are continuous processes. So how do you differentiate when you are, let's say, 5% or 10% renewable resources? It is not possible to detect a fossil-based versus a chemical recycled styrene monomer, for instance. So in order to have a clean book, the idea is to have the materials mixed physically, but kept separated in bookkeeping. It's the same thing when you have an energy provider at home and you switch on the light. It's not green energy that then runs through your circuits. It's just the amount of consumption you as a consumer use will get then added into, let's say, the energy soup. It's the same idea here. So it is the idea that no entity sells more certified products than it sources, than has been sourced. So if we purchase, let's say, or we convert 1,000 metric ton of recycled styrene monomer, we can at the end sell 1,000 metric ton of polystyrene polymers. We have first plants certified according to ISCC, which is a third-party validation partner. And there will be more plants coming up. But we started with the polystyrene Tessenderlo plant in Belgium, as well as the polycarbonate plant in Stade in Germany. This is how the future can look like, adding renewable, sustainable feedstocks into the existing infrastructure. There's been a press announcement which allows me to talk about the current setup. There are companies around, such as Neste, which treat second generation of waste streams, such as kitchen oils, animal fats, industrial oils, purifies them so that they can be used in crackers, such as BASF runs, to create the styrene monomer. And then that styrene monomer has the same specification as the conventional styrene monomer has. And then with that, you can then make polystyrene, or you could use it into many, many other applications where styrene monomer is one building block. The nice idea about mass balance is that it is considered to be a true drop-in solution. What do I mean by that? It has the exact same performance properties and the same specification, and it complies with the same strict regulatory requirements as the conventional does. Why? Because the specification, let's say the monomers that we add into polymerization plants have the same specification. And that is a very appealing route to bring sustainability into the medical beyond mechanical recycling, clean recycling, super clean recycling, and dissolution. So, as a summary, we have seen that polystyrene is already available through dissolution today. It is on the edge to become certified with food contact compliance. And it is also available through mass balanced bio-based solution, let's say, or mass balanced, attributed mass balanced credited, you could say. ABS is then the next building block, or let's say the next platform where we believe this will be of benefit. And then I could say with having bio-based styrene and bio-based acrylonitrile, the first CO2 footprint calculations we made internally demonstrate that a total of 71 CO2 footprint reduction can be created. This obviously opens up with more chemical recycling coming on board, and there is more and more options for the use of recycled styrene monomer. Polycarbonates, where chemical recycling is more challenging, most likely will be available short-term with mass balance. And also TPE, you can see the link with styrene monomer, will be available not only with today's bio-based versions. Think about bio-based TPU, where the polyol is bio-based, or think about TPE, where the polymeric phase can be sourced bio-based, but also with mass balance in the future. So you can see when it comes to circularity, more and more options are opening up. This achievement allowed us to rank quite high as sustainable leaders within the material fields. Here are some examples of rankings we've achieved throughout different industry surveys. And of course, that's all nice to have, but it all lives with customers asking and demanding it. So by that, I'd like to thank you for your attention and I'd like to invite you to ask questions so that we can enter a little bit into a dialogue. Thank you for your attention.
Okay, hey, thank you for that, Ben. That was really interesting stuff. I learned myself quite a bit from listening. So, and we do have a number of questions. We have about 8 or 9 minutes to go into some questions that we don't get to. We'll try to address them in the panel discussion. Let me just start out with one that is actually a rather specific one, if I may. There's a question from the audience regarding USP 88 approval. I don't know if you're familiar with that specific approval terminology, but the question is are there any plans to have chemical recycled polycarbonate or ABS, the so-called USP 88 approvals? I don't know if you're familiar with that terminology or not, but if you are, can you address that?
Yes, most likely the let's give a complete answer here. I think chemical recycling is fairly new to the medical field as it is to the industry. So I think also notified bodies have to get familiar with the terms, what it implies. From a technical point of view, we believe that the testing that we've conducted, including ISO 10993 and USP testing, will also be applied to these, let's say, bio-accredited sources. That, however, I think will be an interesting discussion to have with the FDA or other bodies, what they think. But in general terms, from a technical point of view, I don't see any obstacles why they should not comply.
Okay, thank you for that. Another question, Ben, I'm sorry, I'm getting to some specific ones here, but you're fielding them nicely. So next question has to do with the ISCC certification. I'll just read the question. Would the ISCC, here it says concept, require that all parts of the value chain, including converters, molders, etc., need to be certified as well in order to fully implement circularity?
In an ideal world, yes. That also gives you the credibility of a third-party validation. And when we say our materials are ISC certified, that means that the supply chain up to us is already certified, as demonstrated in the example of polystyrene. Now, of course, that is an extra validation step. An audit has to happen. It's extra cost involved, whether you do some. It's your company decision whether you would like to comply. We strongly advocate it. I think it brings credibility to the industry. However, it's not a showstopper for us. We still continue to supply, but you can obviously not use the ISCC logo nor their statements for your marketing or market communication.
Okay, thank you for that. Another question related to the different types of polystyrenes. Is there any difference in terms of recyclability when you're comparing different types of polystyrenes, GPPS, HIPS, EPS? Any differences in terms of recyclability?
Yeah, I think if you look in from an economical point of view, the great majority of polystyrene applications are indeed dairy product packaging and insulation boards, where you would have, if we stay in packaging, you would have usually a mix of high impact polystyrene with general purpose polystyrene for yogurt packaging, for instance. And in insulation boards, it is very common to use flame retardant additives, and not to talk about colorants and processing aids. So indeed, the nice thing about these processes, these technologies that come available now, is that all the contaminants can be distracted, and you retain only the styrene monomer or the polystyrene chain. I've also mentioned that the sorting, which is mostly domestic household sorting, achieves already a purity of 97% when it enters into our suppliers. So that obviously gives you a really good starting point. And then indeed, it is in the intention within the different routes to separate out all the contaminants that are potentially in polystyrene, as I just mentioned.
Okay, thank you for that. Another question relates to polystyrene and the LCA studies. Something I observed. I was a little bit surprised when you made the comparison of chemical and mechanical in terms of CO2 footprint. Surprised in a positive way, because the actual differences that you presented there between mechanical and chemical are present, but they're actually rather small.
That's true. Yeah,
that's surprising.
And that might be unique to polystyrene because its depolarization route is so easy to implement. What about parking this to the panel discussion? Let's get Marcus' input first. What do you think about other polymers, how applicable that is? I think it might be a island solution for polystyrene primarily.
Okay, that's a good one. That's a good one. Thank you. A more straightforward question: how many times can polystyrene be mechanically recycled? Do you have an idea of that yourself?
No, and of course it depends on whether you start from injection molding or an extrusion grade. But eventually, what happens with mechanical recycling, you chop down the polymer chain, and the more you do that, the more you lose on mechanical properties. Is it now 3%, 5%, 8% that you lose per recycle? That's not available to me, but yeah.
Okay, then I'll ask one last question, and then we'll move on to the next speaker, and then we'll try to address some of these others indeed during the panel discussion, Ben. Here's one from someone. Hey, hi Ben, great talk. So you're getting a lot of positive feedback. Thank you. Do you think it's possible to have already the same quality of recycled plastic material that's needed in the medical sector? Or do you think that there could be issues with, if you will, inconsistency of the product? I think I know the answer to this one, but
medical plastic waste is not any different from domestic plastic waste. So, I mean, it's a question of economic viability. Where do you first find sufficient polystyrene? In the graphic I showed about the distribution within the polymer chains, obviously the polyolefins take a very dominant position. When you believe you have, let's say in laboratory where a lot of petri dishes and cuvettes are made from polystyrene, you could find a sufficient amount of polystyrene that allows us to sort it and feed it back. There is no technical hurdle why not to use that waste stream. It's more a commercial business case decision whether that can be implemented short term.
You know, I'm just a quick comment on my side. This is not really exactly touching on what you said, but something that comes up is when we talk about. There are some questions in the list here that touch on this about how can you implement plastics that are made using chemically recycled feedstocks. Is this really safe or not? And the way I answer that question is saying polyolefins is that, well, ethylene is ethylene is ethylene, propylene is propylene is propylene, and so if you chemically recycle, say, polyolefins back to feedstocks that you convert to monomers, these monomers are literally exactly the same as monomers that are derived from fossil-based sources. So okay, well, thank you, Ben, for that.
Thank you also for your great question. Thank you for your attendance.
Yeah, thank you, and we'll come back to you here in the panel in a few minutes. So, okay, so now on to our third speaker, if I may introduce. I'm going to call you Doctor, if I may, Dr. Marco from Argus Green Cycling Technologies. Marco Tomasi Morgano is the Chief Technology Officer for Argus. I will let him describe his company in more detail. What I can say in some of my other activities in the plastics value chain, we see Argus out there as one of the truly innovative chemical recycling technology companies in the landscape. And so it's really good that we have Marco here to talk. Marco, as I said, is Chief Technology Officer for Argus, but at the same time, Marco has worked in this area for many years and is really one of the quite frankly, experts in the technologies of chemical recycling. So we're lucky to have him here today. He has 10 years of experience in thermochemical conversion processes in academia and in industry. Actually has his PhD from Karlsruhe Institute of Technology in Germany in the field of pyrolysis, which is one of the members of the family of technologies for chemical recycling, of course. And so all this being said, Marco, over to you, and we look forward to hearing from you and learning about Arcus.
Thank you very much, John, for the kind introduction, and thank you for calling me doctor. That's always nice. Yeah, so Ben discussed depolymerization of polystyrene. I will look a bit further, and so I will speak about chemical recycling and talking specifically of pyrolysis, which lead me directly to innovative technologies. And if you look at innovative technology in the field of pyrolysis, the story started 2000 years ago. Pyrolysis is one of the oldest technology we have used for charcoal production in ancient times. We had already have to do with the pyrolysis during the oil crisis in the 70s. So as a replacement for fossil crude oil, it didn't go well. In the 80s, we had already have some experience and also bad experience with the pyrolysis and alternative as waste to energy, competing against incineration or electricity production from waste. And then in the 2000s, the focus have been mainly on biomass research. You can see over there our pilot plant at Karlsruhe Institute of Technology, where we use waste biomass to generate transportation fuel through pyrolysis process, gasification, and then conversion into fuels. Probably we finally found the right way to use pyrolysis processes today, converting plastic waste into new feedstock for generating new plastic out of waste. And as you can see, we are, as technology providers, are integrating in Chemical Recycling Europe, where we together try to make the industry established. So I'm an engineer, so I need to go a bit technical on this. So let's have a look at which kind of plastic can be used in pyrolysis processes. Of course, we look mainly at polyolefins, but also at polystyrene. These are preferred polymers we can convert into liquids as new feedstock. But of course, if you are dealing with waste, then you need to deal with contaminations. And therefore, we need to have a look at typical non-hydrocarbon polymers, PET, PC, PVC is an issue, for instance. And in waste, but also in plastic themselves, you always have additives, fillers, pigments, flame retardants have already been mentioned by Ben. And also, if you look at packaging waste, there might be very different kind of contaminations like food waste, biomass, sort of inerts, metals, and so on. This might not be the case for medical plastic waste coming from your production side, but if you go to hospitals, then of course you might have also this kind of contamination in your mixed plastic bag. So what happens to mixed plastic waste within a pyrolysis process? Pyrolysis process is a thermochemical process, so you need heat from an external source. You need to go high with temperature, so some mechanism takes place. You have a heating phase where the material is getting hot. Then if you look at thermoplastic, you will have a melting phase, so with a glass transition phase. And then you will have a kind of liquid where the first cracking reaction takes place. And then there might be an evaporation when the molecules are small enough. And then finally you will have thermal cracking where the larger polymers become smaller and smaller, and then there you might have your monomers like ethylene, propylene, but also a wild mix actually of hydrocarbons from C5 up to larger waxes. So that's the heating part of a pyrolysis process. And then in the second part, you need a cooling medium to reconvert your vapors you produce during pyrolysis into a liquid. And this liquid, which we call pyrolysis oil, is the main product of this kind of process. Of course, we also produce non-condensable gases, which are, again, hydrocarbons, but not condensable at a low temperature or at ambient temperature. Essentially are olefin gases, ethylene and propylene, I've already mentioned. And normally you use these non-condensable gases as a heat source for the process. You will always produce byproducts. The first one is a solid, it's called coke, which is a residual material containing all the inert part in the plastics and contaminants. And of course, if you look at the plastic waste, so you have a waste and you have contaminants going in, and therefore somewhere contaminants has to go out. And the coke is the focus contaminant sink of your pyrolysis process. Most of the time you also produce some reaction water. It comes from reaction with oxygen, specifically if you have oxygen containing polymers like PET. An important thing to mention here, pyrolysis or chemical recycling is an endothermic process, so it requires external energy, which can be from the grid or using one of the products do you have during the process. And as probably you all know, the energy requirement and the robustness of the process are the main bottlenecks to establish such a process. So moving forward, what do we have with the pyrolysis process? So have a look at one feedstock. You see there, what we always do is an elemental analysis, looking specifically on contaminants, so nitrogen, oxygen, sulfur, chlorine, but also inerts like ash. And you see that's a case for a medical plastic waste where contaminants are relatively low, but still too high for new medical application. And on the right side, you see some picture of different medical plastic waste in different forms. So you see some packaging and you see some devices at different particle size after some pretreatment sometimes are required for a chemical recycling process. And finally, on the bottom, you see a typical distribution of products. And what is important to mention here, more than 50% of your input coming in, including contaminants, is converted into the pyrolysis oil, which is finally the recycled feedstock for further conversion afterwards. So Ben already talked about mass balance approach, and for pyrolysis, mass balance is fundamental. There is no other way to recover recycled feedstock. If you look at mixed plastic waste, what happens to pyrolysis oil, or what should happen to pyrolysis oil? It should go into established infrastructure from the petchem industry, like steam cracking, which is the source of ethylene and propylene used for the production of PE and PP. There is only one way to convert pyrolysis oil, and it is to co-feed with fossil naphtha. There is no alternative due to the infrastructure. Steam cracking unit converts millions of tons per year And therefore there is no really alternative to this one. So what happens in a cracking facility? We look at steam cracking, which is the main source, but also other cracking technologies are available and coming up in the future. So you go together with naphtha, you go into the steam cracker, and you produce your monomers. I've already mentioned several times, ethylene, propylene, C4, C5, but you also produce some pyrolysis gasoline, which is a C5 fuels, which cannot be used as a source for new polymers, some fuel gas, and of course, you always have some losses during a cracking process. Ethylene, propylene can be used for polymerization and therefore going forward to extrusion and new plastics. So if you go for pyrolysis process of mixed plastic waste, you mix with fossil naphtha, you go through a cracking process, you generate monomers, which definitely have the same specification of fossil monomers, and therefore you may produce virgin-like plastics out of waste. So next step would be to discuss more into detail how to implement the mass balance approach for recycled feedstock. So we are discussing at the European level 4 possibilities. The first one will be a technical one. So you mix 10% of P oil to 90% of naphtha. You have a yield distribution. We may assume that we will have the same distribution as for naphtha, and therefore 1 of 10 will be in first monomer product. So we will have 10% of recycling content. The same for a second product going through as a feedstock for polymerization, and then we might have some part of pyrolysis oil going to fuel, which cannot be considered recycling at the moment. The other extreme is the free allocation, and so you have 10 of 100 pyrolysis oil, and you assign 10 to 1 polymer monomer. So you might have 100% of recycling content. This excludes the real yield distribution, and therefore this one is not to be considered a way to go, because of course you don't produce 100% of monomers out of pyrolysis oil. And therefore there are two interesting options which are polymer only. So you can assign everything out of pyrolysis oil which goes into polymers or chemicals to 1 single polymer. So you might achieve up to, in this case, as an example, 50% of recycling content, and the rest is gone, so to say. And the second option will be, again, a free allocation, but with the exclusion of fuel production. So you take everything of the yields out of pyrolysis through cracking, going through steam cracking unit, which produce then monomers for plastic production, but also chemicals production. And so you all again have up to 50% of total recycling content distributed into a polymer or into chemicals. We as recycling, as chemical recycling Europe, consider the free allocation with fuel exclusion the most suitable one, since chemicals are also important, not only plastic, and therefore that would be that's currently our position. So, but let's have a look at the medical waste supply chain. So we'll give a look on what can happen to your materials. You produce plastic medical items. You have your quality control. If it passes the quality control, it goes into hospital and is used there. There you have collection of waste, and then you will have an end-of-life conversion process. In Germany, mixed plastic out of hospitals directly goes into waste incineration. So there is no real option for mechanical recycling. Going back to the production, if it doesn't pass your quality control, it's discarded. So your plastic is discarded as production waste. It's collected as at your production site. In Germany, for instance, there is a regulation for commercial waste. It goes through typical sorting facility, and the part of your plastic which can be mechanically recycled will be recycled. Normally, never into a new pharmaceutical application, so we call it downgrading. Where does chemical recycling fit here? So we can take what's today is mechanically recycled. We can take what today is goes to waste incineration, and therefore to establish chemical recycling of mixed plastics, you need to compete with these two established technologies. That's my next slide, which want to have a look at LCA from the point of view of end-of-life technologies. So this is a screen LCA we have done at Arcus a couple of years ago. And there we compare our technology with waste incineration and with mechanical recycling. Each technology receives credits either for production of new feedstock, as in case of chemical recycling, new plastic for mechanical recycling, and electricity or heat mainly for waste incineration. And then if you look at the greenhouse potential there, you see mechanical recycling, it's better than chemical recycling, and therefore we do not want to compete with mechanical recycling. They have a better position, and it's worth for us to say, okay, give us your residues and not take what the potential feedstock for mechanical recycling. But if you compare chemical recycling to thermal recovery or waste incineration, there is a huge advantage for chemical recycling technologies. So we don't want to compete with mechanical recycling. We want to compete with thermal recovery or waste incineration. So let's have a look at the legislative framework. What are the tools of a mechanical recycler? So first, you would like to have a plant. So you need an authorization of construction. In Germany, it's under the National Environmental Protection Law, which regulates waste conversion plants, and makes things quite difficult for chemical recycling, because at the input, we have waste, and in the second part of our plant, we are a chemical plant. And regulations are a little bit different and makes authorization very complex. At Arcus, we have our first authorization received this year. It took us almost 2 years to get to it. Another tool is REACH registration. We produce chemicals, and so we need to go through a REACH registration so we can market our materials. Third, very important, a REACH registration, it's not enough to sell your material, so you need an end of waste status of your product, which is released at local level. So we work at European level, but we also work at local level with your measure of your city, because it is in charge for putting the signature on your end of waste status. That makes, of course, quite complex to get out of it. And of course, we generate an intermediate, and therefore the end of waste is necessary because petchem cannot receive waste as an input. The three on the bottom are also very important. ISCC Plus was already mentioned from Ben, so I don't want to go through it. RED 2 is used today for renewable energy, for instance, for biomass balance. Today, it's not used for chemical recycling of mixed plastic, and cannot be used as it is designed. So it will require huge modification to have also recycling content in transportation fuel out of waste plastic. And a third point is from the point of view of waste managers. It's a recycling quota. Waste manager always says waste goes in the cheapest hole we have, and therefore you need some sort of help for them. Otherwise, they will never go for mechanical recycling. They will never go for chemical recycling. They actually will never go for waste incineration if some support from the government won't be there. And for chemical recycling, it's also important. Otherwise, we are compared to waste incineration and not to and not considered as a recycling technology. So let me give an insight on Arcus. Finally, Arcus was founded in 2016. It's a German-based startup. Till today, we are 6 employees, so we are very small and quite flexible. We have cooperation with KIT, where we design our process out of existing contaminated plastic waste. So we took whatever is available, more or less, because in Germany, at least, you won't get feedstock out of sorted plastic. So there is no way to get the material that today goes to mechanical recycling, and therefore we need to look at contaminated plastic. We had some additives to remove contaminants. For instance, chlorine is a big issue. We generate products and byproduct, coke, contaminant sink, a product gas made of olefin gases, today used in our process for electricity production. But in the future, in 5 to 10 years, and depending on the scale of future plants, can be also used as a feedstock for new plastic again. Because as I mentioned, product gas is mainly made out of olefins gases, which are monomers for new plastic production. Our main product is a pyrolysis oil. We call it Arcus liquid, and this is it's REACH registered. We have the end of waste status, and so we can market and sell to petchem industry, which feed it into their steam cracking facility and produce monomers for new plastic. We are currently building our process demonstration unit in Frankfurt, in Germany. It's a full-scale plant. When it goes to the reactor size, it has a capacity of 4,000 tons per year plastic waste input, which generates about 60 to 65% pyrolysis oil, which means 2,500 tons per year. The plant is full electric, so we are ready for green electricity when it comes at a good price. The plant is designed to get really contaminated plastic waste. We have more than 600 measuring points, so we can balance the plant perfectly. We consider that we have a quite low energy requirement compared to other technologies. I've shown you a screening LCA. We are going for a full-blown LCA once the plant is live. And that's on the right hand side. You can see the what's coming up next. Plant started to be constructed Q2 this year. We are almost done. We will be ready for commissioning by the end of Q1 2022, and we are planning to have 2 more commercial scale plant live in 2024. And with a picture of our construction site, I would like to thank you for your attention, and I'll be glad to respond every of your questions if you have any. Thank you very much.
So, hey, thank you for that, Marco. That's really interesting presentation. You know, and we'll get to the Q&A in a second. I think what I'm going to go ahead and do is open up the Q&A to the full panel. But the first questions, if I may, I'll direct to you, Marco, that are specific to your presentation, if that's okay. Yeah.
Sure.
Let me just see what we have here. Yeah, I'll just read some of these questions that have come up. This one I find interesting. Hi, Marco. What will be which contaminants do you regard as more critical for pyrolysis? So oxygen containing polymers, so oxygen, or other organic materials, say, I don't know, maybe contamination in the plastic from its use. Well, what's most important in terms of contamination?
Sure. If I look at the specification the PETChem has, the response will be chlorine or halogens due to corrosion issues. I think at Arcus we have a technology which can deal with the chlorine, but everything which is not hydrocarbon is a contamination. And you know, in waste management world we talk about percent, and in the PETChem talks about ppm. There are 5 orders of magnitudes in between. So nitrogen, oxygen, chlorine, sulfur are all very important. Out of plastic, main issues today are nitrogen, coming from contamination of or small amounts of polyamides, and chlorine coming from PVC and other halogenated polymers.
Okay.
Oxygen and sulfur are less an issue today.
Okay, that's thanks for that answer. Let's see. I had another one teed up here that I need to find. Oh yeah, well this one was asked actually at the end of the previous presentation, but I think it applies to both Ben and your presentation, Marco, and that is I think we've already touched on a little bit. How do you address the NIAS? So stuff that's not supposed to be there. How do you address that? NIAS.
I'm not sure. I know what's NIAS is.
Oh, okay.
So please give me an introduction on it.
Yeah. You know, I know the acronym. I'm with you, Marco. I know the acronym. I know what it's supposed to mean. It's basically stuff that that's not supposed to be there. But if anyone on the call can say, give me what does NIAS exactly mean? I've lost it too in my head. But it's basically non-intended substances that are present. Yeah.
Sure.
Yeah.
Then I might give a response.
Okay.
Pyrolysis is a thermochemical process. What we mainly do is to destroy large molecules. So if we have non-intended substances, we will destroy them.
Okay.
To small monomers, and we will finally have parts of it in the liquid. These parts are not hazardous anymore, if they were at the beginning, and finally, when it goes through a secondary upgrading process like steam cracking, that will be completely gone.
Okay. Okay. Well, was a good answer to my question. Thank you for that. I think what I'm going to do, looking at the clock here, is I'm going to go ahead and open up the questions now to the panel. So everyone that's has spoken. And so what I'm going to do, we'll have to experiment with how we're going to do this. I'll ask a question, and then basically whoever is first to start answering, just go for it, okay? Because we don't have a huge panel, so just go for answering the questions when you if you have the answer. Okay. Okay, here's one that I'm trying to. How does medical plastic waste pyrolysis conversion process? So using pyrolysis to convert medical plastic waste efficiently compare to those of other waste streams. So I guess if you're saying you have a waste stream that's basically sourced from a medical plastics stream, how would that compare if you were working with other waste streams? I think I could hazard an answer on that, but go for that. Go for that. Whoever can do that.
I guess it's my turn.
Yeah,
on plastics and on pyrolysis. Consider that the most of medical plastic waste is polyolefins and polystyrene. So if it goes through a pyrolysis process, it's close to mixed plastic waste out of packaging composition, and therefore the product yield will be in the same range. I've shown you some result at bench scale, 55% mass percent. At a larger scale will be a bit higher. Around the typical value you can hear 60 to 65 weight percent of medical plastic waste will be converted into pyrolysis oil, and therefore is a feedstock for.
Okay. Okay, here's a question for the panel, and on this I'd have to include myself in the panel, but I'm hoping the panel can reinforce here. In preparing this webinar, one thing I also noticed is that we would be talking a lot about pyrolysis, talking about depolymerization, these different technologies in chemical recycling, and these address typically different families of polymers: polystyrene, condensation polymers for depolymerization, and then polyolefins mainly with pyrolysis, but other materials too. We haven't talked about another very common medical plastic, and that's PVC. The question is, okay, the presence of PVC as a material in MedPharmPlast's value chain is obviously significant. Can anyone say something about treatment methods that would be applicable for PVC, chemical recycling wise? Like I said, it's beyond the scope of the technologies we talked about so far, but nonetheless, can someone say something about, from your point of view, how would you see the handling of PVC moving forward?
To contribute, I think this goes again to Marco, if you may.
Oh, poor Marco.
Not familiar with PVC recycling.
Sure. If you have 100% PVC, pyrolysis is not your solution. There are more efficient ones to recover PVC. I'm not sure these technologies are economically feasible. I can shortly mention that what we see with PVC in mixed plastic waste is that we might have up to 10% somewhere, which means 4 mass percent of chlorine, which is the issue, of course, as an halogen. So we see PVC as a contaminant. Let me put it this way: different pyrolysis, chemical recycling technology can deal with different amount of PVC. I think at Arcos we can handle a bit more than the other ones. Our proof of concept was made a couple of years ago at KIT with 10% PVC.
Okay, well, thanks for that answer, Marco. And in the meantime, I'm looking at the questions, and we have a very smart gentleman out there in the crowd who says PVC can be recycled within the frame of mechanical recycling as they are orthophthalic plasticizer DEHP free. So for those who are PVC experts out there, that will mean something to no doubt. So, okay, let's see. Let me go to some other questions here. Yeah, here's a kind of a commercial question. I find this also a very interesting one, and I don't know if we can't answer the question, but maybe we can at least touch on it. Do we have any ideas about price points? If you look at bio-based, say bio-based materials, chemical recycled materials, conventional materials. Let me just look here, like at chemical recycled feedstock to make polymers to make for medical applications versus fossil-based feedstock to make polymers for medical. I guess this maybe is beyond the scope of today's discussion because we're really talking technology and not commercial matters. But does anyone have any feel for maybe Ben, you working in a chemical company, maybe any feel for how the pricing points of chemical recycling based polymers versus conventional?
Yeah, I can take that question, John. I can speak for polystyrene, which is the far more advanced polymer within our portfolio. And first of all, I think it's crystal clear that nobody who engages in this journey of sustainability is aware or is unaware of the fact that any bio-based or sustainable business concept will be cheaper than today's. I think that's just to set the scene here. If it was, or to be on the same spot, then everybody would do it. We wouldn't have to have any webinars to talk about these new technologies. So there is a premium applied to it, and that's clear. Now, of course, there will always be a question on supply and demand. That will rule pricing. And at this moment in time, I showed a slide where significant capacity is building up. That's not on stream yet. So there is a premium applied to polystyrene, but it's not in the magnitude of factor 2 or factor 3 anymore. Across that board, and it's been less than that. But let's be honest, until significant volume will be available, I wouldn't expect any close price levels within the next 3 to 5 years.
Okay, hey, thank you for that answer, Ben. That was good. I got another question that maybe for Marco and Ben, maybe Lacey as well. But then I definitely have a question that I want to bring over to Lacey. But this first one has to do with the CO2 footprint. I think both Marco and Ben have talked about this, and this is a question that's in my mind quite a bit too. And I know it's in some other of the speakers as well. And that is, when you look at the different technologies. Comparing virgin material to recycled materials, what CO2 footprint reductions can be expected? I can already answer a little bit of that in saying that there exists already in the public domain a number of LCAs that make a basic comparison of the technologies to virgin material, and I don't have the numbers in my head, but that the gentleman asking that question, please email me and we'll follow up with that. But maybe Marco, maybe Ben, maybe Lacey, if you have any comments on that, how would you generally position chemical recycling technology, type of say depolymerization, pyrolysis, with respect to carbon footprint compared to the virgin-based baseline, let's say?
Would you like to start, Marco?
No, please.
Okay.
First.
Well, that's fine. I mean, I've presented some numbers that were not created by Trinseo, but by a third-party institute, Neue Materialien Bayreuth. And in that study, they demonstrated for polystyrene that the CO2 savings were 80 to 75% coming from super clean mechanical recycling, dissolution, and depolymerization. So there are significant savings. So for the etheric technology, I think we have quite some decent validated numbers, although a peer review is still pending. But I think for the etheric technologies, these are fairly environmentally friendly improvements, I would say. Now, having said that, this might be applicable to polystyrene, and we'll see how that plays out with other polymers. But in general terms, yeah, these are very good indications that we're moving into we're driving the industry together to a more sustainable business model. Would you like to add when it comes to pyrolysis, Marco?
Yeah. First, a general response. Yeah? Mechanical recycling is non-energy intensive solution, and therefore we'll have the best results. And if you increase with, I call it aggressivity of the process, so mechanical recycling, dissolution, depolymerization, and finally pyrolysis, the save in terms of CO2 will be reduced. Yeah. So you mentioned the number for polystyrene for mixed plastic waste will be less. How much less? I can't tell you. I don't know. It's definitely less because pyrolysis, it's a more aggressive and more energy intensive process. But net from fossil to chemical recycling, there will be definitely a save.
Okay, great. Thank you for that. Good. Thank you for that response. So now a question that I say it's a question for Lacey. It was certainly the question is inspired by Lacey's talk some time ago here, and that was when you made the comment about not having design and sustainability be something that you add on at the end of a development process. I find that really very interesting because myself coming out of the polymers industry, I go back say 20 years ago, 25 maybe, so in the mid 90s, late 90s, something like that, developing polymers, some for medical plastics, but all other types of applications. I can say these are working at companies like Borealis and Dow, so leading companies. That the talk of sustainability was just non-existent. Meaning those who are developing solutions, it was just something that never crossed our mind. I cannot recall a single conversation on sustainability back in the mid to late 90s at these companies. And now today, these companies, as we all know, I mean, they have departments, they have huge budgets that are going into this. And this is not altruism. This is not the goodness of the heart, is it? It's because it's becoming of critical importance for the viability of the business moving forward. So that's just a comment. And then Lacey, my question to you is when you look at your Cytiva looks at your customers, how much is it kind of a push-pull situation where Cytiva and say your peers are going out to your customers and saying, hey, let me talk to you about how we're designing our products, designing in sustainability. Let me talk to you about how we would recommend that you handle our products once they are used for your applications. How much is it that you as a supplier are, if you will, being proactive or needing to do that versus how much is it that you're being pulled into these matters by the market that you're serving?
I would say at this point it's probably more being pulled. So we're being reactive to those requests from our customers, but there are product managers, there are account managers who are driving the conversations with customers as well. Like we've sourced a mechanical solution for plastic recycling in the US. Let us tell you about it. But this is something that we have to expand the conversation on. We have to be proactive, especially, like I said, when it takes multiple years to potentially design out waste or change a plastic type that we're using in one of our consumables. So this is part of the business transformation that we have to make. We have to start thinking about what other solutions we can provide, and then testing those with, you know, specific customers and impact customers, and work together with them on changing the product design.
Okay. Okay, thank you for that, Lacey. Another question. This one is going straight to Ben. Yeah. How do TPUs compare to styrenics in terms of potential for future sustainability? Good question.
Well, they're, I would say, fairly different polymers, and they're used in fairly different applications. TPU is one polymer within the TPE, the thermoplastic elastomers, consisting of 3 components: the MDI, isocyanate, then the chain extender, which tends to be a butanediol, and then also then the polyol, which can be in polyester or polyester, or others. In comparison to that, polystyrene is a fairly simple homopolymer, transparent, fairly rigid, and TPU is soft. It's used for footwear application, foot soles, for instance, or lay flat hoses, moving robot cables. So it's difficult to, I think it's an apple to pear comparison, to be honest, from an application point of view. You can't interchange one by the other. From a polymeric structure point of view, as I mentioned, polystyrene is fairly simple. I've demonstrated today that there are multiple approaches to bring a circular polystyrene up and running. TPU, as it consists of 3 components, is more complex, not only in sorting the different fraction, it also has different hardnesses, so that the balance of these 3 components always are different. So I would say TPU is a challenging polymer to be recycled, yeah, it will take us more time to think about a recycling idea. What is currently up and running, what is already available, is a bio-based component. It's the soft segment that is already available bio-based, so you can achieve, let's say, a redundance or a reduction of your fossil-based feedstocks by 40 to 60%. That is already possible today. But on recycling, I think there are multiple funded research projects how to look into recycling of TPU, as it is so broadly used. But from a technology point of view, it's far more complex than polystyrene.
Okay, hey, thank you for that, Ben. I'm down to the 1-minute warning here, so I don't want to go over by more than 2 or 3 or 4 minutes to respect the participants. But this question is also something that's come. I think this is really an interesting one. Medical plastic waste is very often contaminated with blood, virus, germs, etc. We all know this, and also medical plastic MedPharmPlast. That can also be contaminated with what is this, the active ingredient, pharmaceutical active ingredients. It can be contaminated with other substrates, so on and so forth. So are there already strategies on how to bring this waste into recycling companies? And here we're talking, of course, chemical recycling, and proceed without risk towards the environment. So anyone, Marco, Ben, or Lacey, have anything to say on this, and then we'll have to wrap up.
I might say something,
something
on this.
I cannot.
So depends. Yeah, depends on which kind of ingredient you have. Are there solids? Are there liquids? Can be converted chemically into smaller molecules, especially hydrocarbons. Of course, there are several strategies. Yeah? The first one would be to wash them out. That's a classical also for mechanical recycling, which definitely makes sense. Of course, you might still have small impurities, and as I mentioned, chemical recycling, especially pyrolysis, or even more aggressive like gasification, are technology we tend to destroy stuff. And the same fate will will be achieved also by this kind of contaminations. So in my experience, it always ends up in very small molecules. So you also sometimes lose completely the footprint of your original material.
Okay.
Yeah. One comment, if I may.
Yes.
Hospital waste, there are technologies out there to treat it, sterilize it afterwards, and then you have a high quality of plastic recycling, which you can easily treat. So I think there is little to worry when it comes to blood contaminants or drug contaminants. These can be easily sorted out. I think technology is out there. That's really not a bottleneck.
That's really, sorry, go ahead, Lacey.
Sorry, I wanted to make a comment. I think the challenge, I think the technology can handle biocontamination, but I think the challenge with dealing with contamination like bodily fluids is how do you transport this material? And that's really where, like me as somebody who's creating that waste, how do I get my waste vendor to manage my biohazard material with the correct permitting to take it where it needs to go to be chemically or recycled? It doesn't matter what type of recycling, right? And I think that's the challenge with biocontamination from my perspective, at least what I've learned, since earlier in this year.
I see hear what you're saying, Lacey, and I tend to agree based also some of my experiences in recent months. Of it is indeed it's the handling of this from point A to point B that needs to be addressed. Okay, hey, thank you for this this webinar today. I have one last little comment I want to make. I think this is important, and it touches on what Marco had in one of his slides, talking about the origins of the word pyrolysis being Greek, and pyro related to fire, of course. I'm a chemical engineer, and when I first heard the word pyrolysis a year and a half ago, after have not been deep in technology for years and years and years, what is the image that comes into my mind? Fire, right? Exactly, fire. And why am I bringing this point up is because the chemical recycling industry, very much, certainly the pyrolysis folks, are, quote, competing with incineration, right? And those who are practicing incineration, some of those are very happy to muddy the waters. And what they want to do is basically equate incineration with pyrolysis. And it's an unfortunate reality, but part of what has to take place is educating the value chain. So in this case, the MedPharmPlast sector, I think these guys are very smart. They know, but to make sure that they don't buy into this kind of misperception that pyrolysis is burning of plastics. Incineration is the burning of plastics, and that's what we want to get away from over time. So thank you for letting me go on my little hobby horse there. So I want to thank the speakers, all three of you. Thank you very much. I'm very lucky because I'm sitting here listening and learning every minute from people like you, and I'm sure that our participants share that. And I want to thank the participants most of all for taking the time today to join in. And I do not have all the answers to the questions. There are still really a number of unanswered questions that have been posted. I will see if I can save these questions and those who have asked the question, and then over time start coming back to you with some answers that were not given today based on the fact that I was just not able to ask all the questions. So thank you, everyone, and have a happy holidays, and look forward to working with people on this webinar in 2022. So, Lila, you have something to close on?
No. Just please send us questions if you have, and become a member if you are interested. We are more than happy to welcome new members of MedPharmPlast Europe. So happy holidays. Thank you very much, and see you next year, hopefully.
Yep.
Thank you very much.
you.
Thank you very much.
Thank you.
Bye.
Bye-bye.
Bye.
Bye.